Okay, so I connected the current probe and the voltage positive, negative, and I think. And is this showing? Oh no, where's the white spot? Oh, it came off. I touched it. Did it really come off? Yeah, I touched it and it came off. Well, it doesn't matter. You get the idea. We'll be able to see temperature change despite the fact that we don't have that. So now we want to excite it. I'm just going to use the voltage monitor here because that's sort of easier. You don't have to put up any more probes if you're not looking for. Here we go. There's the voltage monitor, channel 1. I have to enable channel B. No signal is found. That's something. This happens over time. Okay, here resistance down all the way. Let's put it down all the way. No signal was found. That's not so good because is this going properly to here? This going to the output. This is the output. This is going to the channel B. This channel B is going to the output. It says positive and negative. I don't know what this. Did something change here? There we go. We have signal. And this channel is 100 to 1. So right now I have 50 volts applied. Okay, I'm applying 14 volts right now. And I'm actually gonna set this. This is. Hey, what's this one again? It's 0.5. It's 0.2, right? 0.2 is to 1 for only one for no loops, right? There's no loops here. Okay, and what is it for loops? 2 to 1, right? Okay. So we actually calculate power today. Let's see how much. So well, I'm actually going to change this is the amps, 5 volts per amp. No, we want, what is it? We want 0.2 volts per amp, right? And then with the first channel, I change it to 100 to 1. So then I'll change this to average. Okay, so now we'll get some, and we have how many volts? We have 10 volts, so that's okay. Hey, you guys don't want to watch the camera? Okay, here's this. I want to change this. Okay. See, look what happens when I move my hand. What frequency is it?
40.
Hey, you guys don't want to watch? Okay, we're changing the frequency, and we're going to get to the resonance. See, the current is increasing as I'm getting closer to the resonance frequency. I think we can auto set it again. And we'll do power too. How about that? Power. Multiplication of channel 1 and channel 2, and it's in power, and I want to take the average value of channel 2 here. Average value, please. Average. Negative power. That's not true though, because it's just the phase. That's the phase. That's it. That's that. It's still going. It's still giving us. No, it's not giving, I'm doing the average of the wrong channel. I did average of channel 2. Let's see, we're doing average of the math channel. I'm doing average of math. Measure average clipped. So I need to readjust this scale here. Okay. I'm using 1.2 watts right now. It seems to be getting a little bit hotter. I should have showed the temperature now. Well, we're gonna see 1.2 watts to the sample right now. It's we're not at resonance. We're past resonance here. Let me just use this one. You want to touch it? Feel it. It feels smooth now. If you touch it, it feels smoother. Touch it. It's ground. It's ground. I hope this doesn't fall. No, like honestly. It's only like how many volts? 10 volts? It's like a battery. Anyways, look. I should have do a thing now. I should have told you the temp. I should have made a temperature thing. So I'll just draw this box here. So this box is it says it's how much? What's the temperature of the box? It's 18.2. So it'll warm up. It just takes time. See, look in the middle. It looks like it's warming up now. Let me just get this. 18.2 is the box temperature. So it's getting hotter. It's better to put something behind, so you can sort of tell the temperature better. Like if you go like this or something. So you can't be changing your setup because the temperature may change. This is what I was talking about, difference in temperature and things like that. So, where I'm actually not satisfied right now. I want to get it hotter. I didn't measure the vibration yet, but I want to get it clearly so it's a big difference in temperature, and we'll just keep cranking it up until it happens. It's saying it then. It's saying the math channel. Okay, it's about 3 watts now. So right now the temperature at the hottest point, which is probably, so now it's like getting hotter. I want it to get even hotter. Now this is double the temperature.
It smells.
It smells? Now the watt is 5 watts. So hopefully it won't blow up. But see, you can see the middle is heating up now. It just depends on like, see, the whole thing is heated.
You're gonna change the color?
To that rainbow one? We can do watch. We can do some cool thing. We can change the scale.
Yeah.
So there, only the dark one will show. So that's about 4 or 5 watts here. It's not getting so hot, which is good. But here's 5 watts, and I'll try to get back to resonance. I think there's a little bit of whiteout right here. Or is it, what's there anyway? No, it's glue. It's like epoxy that's just like spilled over. So that's if you see it heating up. This is not as interesting as when you heat up the sample, which we're going to do next. We're going to heat up a sample and you can tell the temperature distribution as maybe you've seen in the pictures. So this is hot. It's over 8 watts, I think, right now. It's over 8 watts. Here, it's about. Wow, it's actually quite hot. I'm surprised it's not blowing up. Right now, if you check the temperature is only it's 24 degrees, so it heated up 5 degrees. I think what was the original room temperature? 16.
16.
So it heated up about 10 degrees. But for our little because this is a huge ceramic though. If you think about the massive our ceramics that we were using for testing versus this one, this is actually quite thick and quite massive. So, and also because these metal things are touching, I feel like the metal's getting a little hot too now. See, the metal's starting to show. The reason it's starting to show because it's relatively getting hotter and it's getting in that range. What was I gonna say? The reason why it's also cooling down because it's touching something. The metal pieces are acting as heat sinks. Therefore, it's able to cool much better than our samples, which are just in free air. Okay. Now we're gonna hook up. Now we're gonna actually turn this down to look off resonance. So now we'll try the sample, and I'll just show you the same thing on the sample. So you can, from here you can record values. You can take a picture of the sample. Is it still recording? Yeah, you can take a picture here. Image, is it still recording? Make sure it doesn't like. Yeah, you can say, if you go to image, recording, record one image. And you can go into settings, image, settings, and it'll tell you, somewhere you can figure out how do you want to save your image. Or you save your image, or you can export it. You can export it as like values. So it'll give you an Excel chart. Each pixel will be one cell in the sheet, one cell in the Excel page, and each square will tell you the number. So it'll be like number 26, 26.2, 26.4, and then it'll tell you everything like that. So you can sort of get that. I don't know if I have it on my home page here. Image of heated rod here at 350 millimeters per second. And while that's happening, you want to touch it? I don't want it to shock me. I don't know if it will. This is conductive, right? That's done. That's so hot. I didn't hurt it that much. It's a little bit warm. A little warm. Okay, that doesn't look like an image of a heated rod. Anyways, now we're gonna go for this. So these are the classic samples that we use to demonstrate. Okay, that doesn't look like a heated rod to me. These are the classic. But maybe I can show you that, or you can try to figure it out. Just know that menu I use to save the image. You can also let's just do it right now because it's actually quite important, I think. Image, save as, and you can save as an IR file. You can save as bitmap, a picture, CSV file. That's what you want. And when you upload it, you can sort of highlight all the cells. And if you write color code, you know color coding in cells. You did it, right? Yeah. She had her famous interpretation of the impedance and colors. You should just put colors on there. Okay. Anyways, you can do that. You can have fun like that. You can change the colors, and you can actually tell. See that picture right there? See that picture on the iCat poster? Yeah, that's the same thing. That's from Excel. I converted pictures. You convert the picture, the numbers to colors, and it comes out like that if you zoom out a lot. Okay. So this is the sample that we're using here. It's coded in white because you can tell the temperature. This is 2 millimeters thick. You can get the temperature from it. It's sort of thick enough. But for your smaller samples, you may want to look at the top. The sample holder is going to draw heat away, so you're going to have a dent. I don't know if you watched the video I posted, probably not, it's too soon. But it's going to have a dent. For the time being, this is a sample holder, I think it's showing here. This is a sample holder. I'm going to be putting the samples between two electrodes. I'm going to be flipping it around. So it's going to be in like that. So I'm going to be flipping it around now. Once I put it in, I'll flip it around. I probably should measure the vibration velocity just so I can get an idea. Oh, it's really big. So whenever people come to our lab for a demonstration, we do this. Actually, this is not good because I'm going to be flipping it around. So it's not the best. We'll probably run it something. Okay. I don't really care so much about the, I don't really care that much about the current because we can measure vibration. Vibration can tell us the resonance frequency, so you don't need the current for this demonstration. How's the signal looking? Not good. That's good enough. And it's plugged in, isn't it? Okay, it's plugged in channel 3. Voltage needs to be applied here. So I'll just hook it up. And here it doesn't matter because none of these are connected to ground. So You can put your ground whatever you want. Or actually, might as well have good practice. I don't know. I'll put the ground closer to the ground. So now this, now you can't see anything, right? So I'm just gonna press this candle button here to refocus. This is a candle thing that looks like a candle. So refocus everything. It'll look like that. Let's go back to here. It doesn't look so focused so well, does it? So I will probably just adjust this. Usually I look at the camera and I move it around. I actually first start by zooming in, getting closer. I think we can do that. I think you saw there's a zoom, yeah. Zoom, I'll just zoom in the middle right now. So that's that. Basically, that's really bad. That's about as good as you're gonna get, honestly. Unfortunately, that's about. You can put your hand here. If you put something hot in the back, samples the room temperature, you sort of create a contrast. But I think as we okay, it's not exiting this menu. As we, and I think I forgot to mention the shutter. I mentioned the shutter that makes sort of a. This is auto shutter is on. But I think we turn off initial. You see that clicking sound? That's called the shutter, and sort of readjust the temperature. So before you start taking measurements, you want to have that done. For some reason, it's not doing it automatically. Usually, it does all the time automatically. You can also focus using these buttons here on the corner. Noise reduction on. What happens when you turn it off? It gets more noisy. Okay. There's a bunch of little features here. You can also record videos with this, and you can analyze videos later. Videos just multiple pictures. Then we want to start the sample voltage. So we'll just start it up here. Channel B. We're at 3.6. We're at what? How many volts? 20 volts. That's okay. And I'm not getting any vibration here because it's not. And we're gonna have it on 125. Well, no, actually we'll have it on 1,000. And we want to find. And I'm gonna actually take the RMS value of channel 3 here, so I can know how fast it's going. Okay. Huh? Oh, don't touch it necessarily. Yeah, you have to hook it right here. That's good. That's not good. Yeah, you can just press this button easily just to turn off and on the signals. So I want to get the quick measure. I want to measure channel 3's RMS value, and that's 24, so that's really small. And that's 1,000. Okay, that's okay though. Okay, I'll just readjust this here. Right now I'm at 200 millimeters per second. It's not hot enough for me. Yeah. Okay. So for this sample, what happens when it's driven at resonance? What happens to the vibration velocity? Is it in phase, out of phase, opposite?
Out of phase.
The displacement is exactly opposite, 180 degrees, and the velocity, I think it lags. Technically, it lags 90 degrees behind, so it's like 270 or something like that. So it's opposite and then lagging. So if you take the integral, you'll have the displacement. Right now we're at 340. See, look, now it's heating up. Okay, look. And if you want to do your initial adjustment, you want to do when the sample's a little bit hot, so you can sort of get an idea here. So now it's heating up. Let's stop this autofocus thingy. Let me give you this little bit like that. See, that's the sign. That's the distribution. If you want to get a line, for example, I can just draw a line across here, and you can get a distribution. It's called profile. Right now, depending on how well I adjust this thing, it's going to do. The line's a little bit. I gotta scoot it this way apparently, like this way. Now it's more in the middle, sort of. So there's that's the first mode. You see how the temperatures are more in the middle. This little loop thing, I think it's just because of the way it's angled. I don't think it actually reflects the temperature here. Let me just look at the main picture. Something looks to be in the way of this. Maybe because I touched it. No. I don't know why. If that part was on that side. I don't know. I couldn't say.
But this part does not have the color.
Is it covered? No, it's covered. I think it's covered by these wires. It's covered by the sensor. It's covered by this wire.
Okay.
So, but anyways, it's a sinusoidal distribution thing. I can sort of adjust it so it's not as much as possible. And it's a little better now. It's still covering. Now we'll do the third mode. How many modes? What does it look like? So we'll do the third mode. What's the third mode? Or it's not really the third mode. This is 17. Okay, so now we have the vibration again. So what? Do you expect it to be hotter, or generate more heat or less heat? Okay. Oh wow, why is that?
The signal
It's okay. I just need the measurement. I don't need the best signal. It still works. So slowly over time, it's going to develop now into 3 modes. See these little 3 nodes? They're not shown so well right now, but you get the idea. If I move these wires out of the way, adjust this perfectly on. If you have this thermal camera a little bit off, it's going to show a little bit skewed. This is going to be skewed a little bit based on, because this side will be closer than this side, and it's sort of how that distribution. But basically, you have 3 nodes here. The strain maximum is here, strain maximum here, strain is maximum here. There's a heat generation, heat dissipation. It's 30 degrees, which is about 15 degrees higher than room temperature. Is there anything else? You can save the image. Oh yeah, see this top part of this top part right here. I painted it with whiteout. I think somebody glued the wire over it, so you may want to put the bottom part as whiteout. But I actually measured the temperature from the back. This is why this hole is here, so you can measure the temperature from the back of the sample. And I put the 88 tape all around it, so pretty much you can use any of this part as a reference temperature, and that'll work for you if you want to have the 0.95. So I think if you save an image or you save a video, this is the only program that can open it. Maybe you have to export it to a different file type. The files are kind of big too. You can have a plot over time. You can look at different measurements here. So is it almost done now? Yeah, I think that. So this is the way we do this. And usually for any different people come for demonstrations, you'll just explain to them this, and you'll explain to them the first mode, and that's the one. So we don't have so many things to show them.
1 millimeter.
What do you say?
1 millimeter. 1.2 millimeter.
I'm sorry?
Do not measure the thickness less than 1.2 millimeter.
Thickness, because that's the smallest dimension. So you can just show them here. If you really get the image, you can sort of get a middle. I think it's either 0.8 or 1.2. I think it was 0.8 because I did actually do it, and I wouldn't have done it if I couldn't do it. So I think this is 0.8 is 1. So then basically, or 0.4 or something like that. I think it was 0.4 millimeters. Therefore, a 1 millimeter sample is too small, because you need at least 3 pixels in order to get one entire pixel on there. Because if you have, one pixel could be, you need 3 to make sure to at least get 100%. High power testing. 1 meter per second. Just throw it. Okay. Anyways, Is there any questions? Yeah, you could hook it up. Erkan had done partially. You put the cable to the output over there to the oscilloscope, and you put a capacitor. I never really did that, but you can sort of monitor the temperature just by looking at it at a certain point. That may be useful. And yeah, heat generation is a good way to know that things are working. Are things heating up, or are things vibrating or not? Do you have any questions? You can do it on use this computer for the program. It has the same program on it. You'll have to take this wire around I may end up donating this computer to the lab because it's sort of useful, but maybe not. So this program is on this computer, and you can also use the monitor if you're not interested in recording an actual image. It's not necessary. You can also set the emissivity values from here directly, and you can do those reflected temperature measurements. So for some reason, if the computer breaks down, you don't have access to the program anymore, you can still do everything from these settings on the top of the thermal camera. So there's another. Excuse me. There's another. So if you do want to measure 1 millimeter, we can actually do it. We have a lens, which is worth a lot of money. The thermal cameras. So this is like a couple. So this lens you can actually put on. You can actually put this lens on here. So just be careful with it and know where it is. If you don't. So the lens looks like this. It's hard to put on. Actually, I don't want this. I want the back cap to come off. So squeeze a little bit. Okay. It's like a germanium lens because it has to be for infrared light. So basically, you put it in here. There's like little pins here. You put it in, and so you can measure the 1 millimeter sample. Huh? It doesn't. It has its internal lens. Like a camera has a lens itself, but then you can put other lens on top of it, and that allows you to get really close and still have focus. It doesn't zoom in. It doesn't zoom in from here. It allows you to just get closer. So it's not going to zoom in. Oops, this should be. This is the case. This is the case for this. So I think I think that's it. This is probably we can put over there. And where's this? I had this box over here. Where's that box? This is the box I put. This is something that we had used before. This is on program for the computer and stuff. You can download that program online. But this measures a single point. It has a laser that comes out of it. It only measures one temperature point. It has a laser that comes out of it, but its minimum size is more than 3 millimeters. So it's sort of like modulate this used here and just read the temperature then. But you can it interfaces with the computer a little bit better. But I don't know about its accuracy, and it's sort of deceptive that when you get really close, there's two lasers that come out to show you where it's measuring. The two lasers get on top of each other. You said, hey, I'm measuring that point exactly, but that's wrong. The minimum size, laser size that you should have, because there's two lasers that come out from here and here, is 3 millimeters. I think it says something in the manual about it. I don't remember because I don't use it, but just know something about this. You can actually use it if you want to measure a single temperature. But I just leave the demo camera stuff in this box. Like this piece of, like this thing. I just keep it there. Probably don't want to keep the lens there. And I just kept this here. This can get hot. I think it heated. I don't know if I did a blow dryer or I think I put it on the hot plate and I heated the whole thing up. And I used this to put a tape on it, and that's how I measured the emissivity of that. If you want to cover your whole sample with that, this white covering, let me just take it out. I actually found, because the electrodes, when they're silver, here, you can turn it off. When the electrodes, when they're silver, they don't emit a lot of light. They reflect light and they don't emit a lot. So actually the sample is hotter. I found at least like 2 or 3 degrees when you put this, when you coat the whole thing with white out. It's actually, the sample actually gets cooler. What I did basically, I put white only here, and then I measured the temperature at a certain vibration velocity, and then I put white all around it. So then it'll emit more light. It'll emit more heat. When it emits light, it's losing heat, so it actually cools it down a little bit. That's interesting to know that it does that. On this sample specifically, since I only have a small part of it exposed, so I can get the electrodes to it, sometimes you may end up on the whiteout and it may not get excited. Therefore, you may think that the sample's broken. The samples don't usually break. You're just probably doing something wrong. I do it all the time. That the exact point is not one part of the electrode's on the whiteout, and it's getting blocked from getting to the electrode. The actual one. Here's the laser, tape, and are there any questions? I think it's okay. Huh? What did you say?